Did you know Venus rotates so slowly that a day there is longer than a year? If you try to stand on Venus, you wouldn't survive even a single second. Not because it's close to the sun, but because the planet itself traps heat like a sealed furnace. Venus is hot enough to melt lead, and its surface temperature is over 460 degrees Celsius, making it the hottest planet in the entire solar system, even hotter than Mercury. Now, here's the surprising part. Venus is not just the hottest planet. It is a world where pressure crushes, clouds burn, and time behaves strangely. When you look up at Venus in the night sky, it shines beautifully. It's bright, calm, almost elegant. That brightness tricks us into thinking it might be pleasant. But nature doesn't care about appearances. The surface of Venus is hidden under thick clouds, and what lies beneath is nothing like the peaceful glow we see. Here's the lesson. Brightness does not mean safety. The planet reflects sunlight strongly, yet still traps enormous heat. That's the paradox. It looks cool from far away, but up close it is overwhelming. Don't judge a world by its glow. Now let me explain something simple. Imagine you leave a car closed in the Sunday. The sunlight enters through the windows, heats the inside, and the heat gets trapped. It keeps building. Venus is like that car, but on a planetary scale. Sunlight enters, heat tries to escape, but the thick atmosphere blocks it from leaving. Over time, more heat gets trapped, and the temperature rises higher and higher. This is called a runaway effect. Once it starts, it feeds itself. Venus shows us something important. When balance is lost, temperature can spiral out of control. Energy balances everything. Now let me tell you something that surprises people even more than the heat. The air on Venus doesn't just burn, it crushes. The pressure at the surface is about 92 times stronger than Earth's. That's like being nearly a kilometer under the ocean, except you're in air instead of water. On Earth, we walk around under one atmosphere of pressure and barely notice it. But on Venus, the air presses down with such force that a human body, or even many machines, would be flattened instantly. Not slowly, instantly. Here's the key idea. Temperature isn't the only danger. Pressure is invisible, but it can be just as lethal. We tend to think of air as light and harmless, but air can behave like a heavy fluid when packed tightly. Venus teaches us that the same substance, atmosphere, can be gentle on one world and overwhelming on another. Never underestimate pressure. Now, imagine looking up at the sky on Venus. You would not see blue. You would see thick, permanent clouds. And those clouds contain sulfuric acid. Yes, the same kind of acid that can burn through metal in a laboratory. On Earth, acid rain can damage forests and buildings. On Venus, the entire upper atmosphere is filled with acid droplets. It rains acid, though it likely evaporates before reaching the ground because of the extreme heat below. The result is a planet wrapped in a corrosive layer from top to bottom. This tells us something profound. Chemistry shapes worlds. It isn't only temperature and gravity. The substances present in the atmosphere decide what is possible. Venus shows how the wrong ingredients, combined with heat, can transform a planet into a hostile environment. Chemistry can change everything. Now, here is something that makes me smile as a physicist. A day on Venus is longer than a year on Venus. That means the planet spins so slowly that it takes more time to rotate once than to orbit the Sunday. Isn't that strange? Venus rotates once every 243 Earth days, while it takes about 225 Earth days to go around the Sunday. So if you stood there, which you cannot, your day would stretch longer than its year. Time would feel completely different. Why does this matter? Because rotation affects climate. On Earth, fast rotation helps distribute heat between day and night. Venus rotates so slowly that one side experiences extremely long exposure to sunlight, while the other side stays in darkness for a very long time. That imbalance adds complexity to an already extreme world. The lesson is simple. Motion shapes environment. When you change how a planet turns, you change how energy moves across its surface. Now let's talk about something even more puzzling. Venus spins in the opposite direction compared to most planets in our solar system. On Venus, the sun would appear to rise in the west and set in the east. That feels wrong to us. But nature doesn't promise to match our intuition. Scientists believe this unusual rotation may have been caused by ancient collisions or long-term atmospheric forces. I won't complicate it with equations. The key idea is that planets can change dramatically over time. What does this teach us? That the early history of a planet matters enormously. A small difference at the beginning, a collision, a tilt, a shift in spin, can shape billions of years of outcome. Venus and Earth started with similar materials, yet they took different paths. That is not magic. That is physics playing out over time. History decides destiny. On Earth, we enjoy seasons because our planet is tilted. That tilt changes how sunlight spreads across the surface during the year. Venus, however, has very little tilt, almost upright. At first, that might sound peaceful. No dramatic seasonal swings, no winter or summer extremes. But here's the twist. When a planet already has trapped heat and crushing pressure, removing seasonal variation doesn't fix the problem, it locks it in place. Venus doesn't experience seasonal relief like Earth does. The environment stays consistently extreme. That consistency is important. Stability is not always comfort. On Venus, conditions remain harsh day after day, year after year. There is no natural cycle to cool things down significantly. This teaches us something about planetary balance. Small geometric details, like tilt, influence how energy is distributed. When sunlight doesn't vary much through the year, the system depends entirely on other mechanisms to regulate temperature. Venus lost that balance long ago. Balance keeps worlds livable. Now let's look beneath the clouds. Venus is covered with enormous volcanic features, vast plains formed by ancient lava flows. Scientists believe the planet has experienced widespread volcanic activity in its past, possibly reshaping large parts of its surface. On Earth, volcanoes release internal heat gradually. That heat escape helps maintain equilibrium. But if too much heat builds up inside a planet and cannot escape properly, it can contribute to surface transformation on a massive scale. Venus shows signs of having undergone such dramatic resurfacing events. Imagine a world where the ground itself has been repeatedly rebuilt by internal fire. That tells us the planet is not static. It is dynamic, powered by deep energy from within. The key insight is simple. Planets are systems. Heat from the inside, heat from the outside, and atmospheric trapping all interact. When those interactions favor accumulation instead of release, conditions intensify. Internal heat shapes the surface. Now you might think Venus is quiet because it has no oceans and no familiar weather like ours, but that would be a mistake. Evidence suggests there is electrical activity in those thick clouds, lightning. Yes, lightning without rain, as we know it. On Earth, lightning forms in storm clouds filled with water droplets. On Venus, the clouds are made of sulfuric acid, yet nature still manages to build electric storms. That tells us something powerful. Electricity does not need a friendly environment. It only needs conditions that allow charge to build up and release. This is a reminder that energy moves. When heat and atmospheric motion create friction, charges separate. When enough charge accumulates, it discharges as lightning. The planet is not calm. It is electrically active, high above its surface. Even in a world already extreme, additional forces operate. That's the complexity of planetary systems. Heat, pressure, chemistry, and electricity all interact. Energy always finds a path. Now let's talk about something deeply important: water. Early Venus likely had much more water in its past. Some evidence suggests it may have even had oceans. So what happened? When sunlight increases surface temperatures, water can evaporate. Water vapor is actually a powerful heat-trapping gas. As more water enters the atmosphere, it traps more heat, which causes more evaporation. This feedback can accelerate warming. Over time, the process can become self-reinforcing, a runaway cycle. Eventually, intense sunlight can also break water molecules apart high in the atmosphere. The lighter hydrogen can escape into space. Once that hydrogen is gone, the planet cannot easily rebuild its water supply. Venus may have lost its water this way. If true, it shows how delicate planetary balance is. A small shift in heat can change an entire ocean world into a dry, hostile one. Water changes everything. It's fascinating to realize that Venus and Earth began their journeys almost like twins. They formed from the same region of the solar system with similar sizes, compositions, and distances from the Sun. Early on, both planets could have had oceans and potentially even temperate conditions. So why the drastic difference today? Tiny initial variations in rotation, atmospheric composition, and volcanic activity snowballed over millions of years. Venus developed a thick carbon dioxide atmosphere, trapped heat, and lost its water, while Earth maintained a balance that allowed life to flourish. This teaches us a vital lesson. Small differences at the start can lead to enormous divergence over time. Evolution of planets is not only about size or distance from the sun. It's about feedback loops, chemical interactions, and subtle historical events that compound relentlessly. If you ever want perspective, look at Venus. Two nearly identical starting points, but one became paradise, the other became a furnace. Tiny changes become enormous consequences. Let's dive a little deeper into the heat problem. Venus's atmosphere isn't just thick, it's a thermal trap. Sunlight enters through the clouds, warms the surface, and tries to radiate back out. But the dense carbon dioxide atmosphere absorbs that outgoing heat, reflecting it back like a blanket. Think of it like standing under a thick winter quilt on a summer day. The energy has nowhere to go, so the surface keeps getting hotter. Add to this the sulfuric acid clouds above, which also reflect sunlight back down, and you get a planet that can't cool itself. The lesson here is surprisingly simple. The physics of reflection and absorption governs temperature. You don't need complex machines to understand it. You just need to see how energy flows and where it gets trapped. This is why Venus reaches 465 degrees Celsius and keeps it steady. Heat accumulates relentlessly, day after day, century after century. Trapped energy defines climate. Now let us imagine something carefully, not dramatically, just physically. Suppose a human somehow stood on the surface of Venus. What would happen? First, the heat. At around 465 degrees Celsius, the temperature is hot enough to melt metals like lead and zinc. Human tissue would not remain stable. But even before heat finishes the job, the pressure would already be overwhelming. With 92 times Earth's atmospheric pressure, the air would press on the body with crushing force. It would feel like being deep under the ocean, except without water to distribute the load safely. And the atmosphere itself is mostly carbon dioxide with clouds of sulfuric acid above. There is no breathable oxygen, no protection, no relief. So the survival time is essentially 0 seconds, not because of one single factor, but because several extreme conditions combine at once. Heat, pressure, and chemistry act together. That combination is what makes Venus so unforgiving. Here is the deeper insight. Danger on a planet is rarely caused by one variable. It is the interaction between variables that creates extreme environments. Venus is a perfect example of compounded effects. Environment determines survival instantly. You might wonder, if humans cannot survive, what about machines? After all, we have sent spacecraft to Venus before. Indeed, several probes have landed there and transmitted data briefly before failing under the harsh conditions. The heat and pressure gradually overwhelm electronics and structural materials. Even specialized engineering has limits when exposed to nearly 465 degrees Celsius and extreme atmospheric force. This shows us something important about technology. Machines are not magic. They obey the same physical laws as everything else. Materials expand under heat, components degrade, and circuits fail when conditions exceed design tolerances. Designing for Venus requires extraordinary preparation, cooling systems, pressure-resistant structures, and short operational expectations. Even then, lifespan is limited. Venus reminds us that engineering success depends entirely on understanding the environment. The better we understand the physics, the better we can design tools to operate within it, even if only briefly. Technology respects physics. Now here's where the story becomes important for you and me. Venus is not just a frightening planet to study, it is a warning written in physics. When we look at its runaway heat, we see what can happen when an atmosphere traps too much energy. When we see its lost water, we understand how delicate oceans can be. I like to think of Venus as a natural experiment. Same general starting conditions as Earth, yet a completely different outcome. That tells us something powerful. Climate systems can tip. When energy in equals energy out, things stay stable. When that balance shifts too far, change accelerates. This is not about politics. It is about energy flow. The same laws apply everywhere. Sunlight arrives. Heat must leave. If it cannot leave efficiently, temperature rises. Venus shows the extreme case of imbalance. Earth shows a working balance, at least for now. So, when we study Venus, we are really studying planetary behavior. And that helps us understand how fragile equilibrium can be. Balance is not automatic, it must be maintained. Now you might think Venus is too harsh to study further, but that would underestimate human curiosity. Scientists continue designing missions to observe it from orbit and analyze its atmosphere in detail. Each new measurement helps us refine our understanding of how such an extreme world evolved. We do not need to land on the surface every time to learn something valuable. Sometimes remote sensing, studying reflected light, atmospheric chemistry, and temperature patterns can reveal enormous insights. That's the beauty of scientific progress. Better instruments allow deeper understanding without direct exposure. Venus remains scientifically important because it represents a possible future for any planet that loses balance. By examining it closely, we improve our models of atmospheric physics and climate behavior. The exploration of Venus is not just about one planet, it is about improving our grasp of nature's rules, and every new discovery reduces mystery. Curiosity expands understanding. Now let me step back and ask something a little philosophical, but still scientific. What does Venus really tell us? To me, it says that planets are not fixed personalities, they are systems. They evolve, they respond to energy, chemistry, and time. Venus shows how a world can shift from potentially Earth-like beginnings into something completely different. That realization is humbling. It reminds us that stability is not guaranteed. It depends on continuous balance. When I think about it, I don't see an evil planet. I see physics working without compromise. Carbon dioxide traps heat. Water vapor amplifies warming. Pressure increases with atmospheric mass. These are not moral choices. They are natural consequences. That perspective is powerful. Fear decreases when understanding increases. Once you see how the mechanisms fit together, Venus becomes less mysterious, but no less extreme. It is a laboratory of planetary behavior, demonstrating what happens when feedback loops dominate. And that knowledge is valuable, because understanding extreme cases helps us understand normal ones. Knowledge replaces fear. So here is the final thought I want to leave you with. Venus is terrifying, but not because it is mysterious. It is terrifying because we understand it. We can measure the temperature. We can measure the pressure. We can map the clouds. And when we put the numbers together, the picture becomes clear. A thick carbon dioxide atmosphere, a runaway greenhouse effect, crushing surface pressure, sulfuric acid clouds, and heat trapped for millions of years. That combination creates survival time of 0 seconds, not by accident, but by physics. And that's the real lesson. The universe does not negotiate. It follows rules. When we understand those rules, we gain power, not over the planet, but over our knowledge of it. Venus stands as a dramatic example of how energy, time, and atmosphere interact. And it reminds us that our own planet's balance is precious. Understand the rules, and you understand the world.